I'd like to introduce Fab Tillier from Microsoft. Fab will give us an update on Network Direct. Thank you.
Hi, folks. I'm sure all of you are thrilled to have Microsoft here. Not our usual place to be, really. But I'm here to kind of talk to you about Network Direct, what we've changed Network Direct, and we just released version 2. What is Network Direct? So Network Direct is RDMA interface that Microsoft defines. A Microsoft-defined RDMA interface. It's being used by Microsoft's MPI library. There's other projects that are toying with using it. The main goal is it provides transparent support across different fabric types: InfiniBand, Rocky, iWarp. Miracom at one point had a network direct provider. I don't know if they still do it. It's all IP addressing based, so it doesn't. It tries to keep the application unaware of subnet management. The key things with Network Direct, the reason that we defined a new interface rather than just adopting one of the existing interfaces, it's first and foremost designed for Windows. What that means is Windows is fundamentally an asynchronous operating system. So asynchronous I/O is something that is exposed all the way to applications always for file I/O, for socket I/O, etc. We wanted to make sure we tied things like connection establishment, right? Lengthy operations, memory registration, completion queue notifications to our asynchronous I/O model, so that if you're trying to use a mix of different I/O technologies like files and sockets and RDMA together, you could use the common APIs for lengthy operations, so you can aggregate completions like that. It's a little bit higher level of abstraction than traditional verbs. Just from merging, from being IP-based connection establishment, you end up not having the intricacies of the IBCM exposed, right? It's all, you have a connect call. You don't modify queue pairs manually. That's all done internally under the covers. Like I mentioned, it's fabric agnostic. It has a stable ABI. We've reused the user mode device framework API model, which is basically leveraging the COM interface models. So you build an interface, they're versioned, every interface has a GUID that represents it. You can query for different interfaces, so it's fairly easily extensible. There's no callbacks. Everything is a pull model. So if you want a notification, you have to explicitly request a notification, and when it completes, that your request completes. We hook the WinSock provider catalog mechanisms to discover providers dynamically, so we don't have a common infrastructure that everyone calls, for better or for worse. And we like to think that's easier to understand and easier to develop for. For asynchronous operations, memory registration, completion queue notifications, and connection management all are Win32 overlapped I/O operations. The client gets to decide how those notifications, when those requests complete, how they're picked up, whether they use an I/O completion port or they wait on this particular I/O. That's completely up to the client application. And because it's all I/O based, from a kernel driver perspective, the kernel drivers don't have to know how the application is picking up the completions. It just completes the I/O request, and the I/O manager does the rest. Now, in Network Direct version 2, which we just released, the big features, they're kind of in order of importance. The first one is support for third-party applications. Third-party here meaning something else than MSMPI. Until now, the MSMPI was the only sanctioned user of Network Direct in user mode. One of the things we ran into when we were working with other groups within Microsoft, external Microsoft, is the interfaces were a little bit restrictive and sometimes required conflicting implementations of the drivers. The second thing, which is probably one of the most important ones, is alignment with the new Network Direct kernel mode interfaces that were launched in Server 2012. One of the benefits of aligning the interfaces like this is it allows IHVs to implement drivers that can support both user mode and kernel mode while sharing a lot of the internal logic, so that you don't end up having a totally separate path for user mode from the path for kernel mode. We fixed the way we can extend the interfaces, so the way you discover new object types in the new version. The old version had the unfortunate effect of if you want to make a change at, you have the object hierarchy, right? You have an adapter, you have protection domain, you have queue pairs. If you want to change a queue pair interface, that ended up bubbling up through the whole hierarchy, and you end up with a whole new set of interfaces, which was not good. We've changed memory registrations, so they're real objects, added shared receive queues, added the ability to, when you create a completion queue or shared receive queue, specify the affinity that you'd like to use. It's not a hard binding requirement, but you can say, all right, if you know your application to be bound to a particular CPU, you can pass that through to the driver to say, hey, my completion queue, if you can affinitize my interrupts to this same core, please do. And that way you can try to take advantage of locality. We've also helped align things a little bit more with the verb standards, both IWARP and InfiniBand, around, for example, inline data request. ND version 1, we had this grandiose idea that it'd be really cool if we could do per SGE inlining. So you could specify on a per SGE basis in a work request whether you wanted to have that data be inline. Turns out it's not widely supported, and that resulted in never being supported. So with NDV2, we moved to saying, all right, it's on a per request basis. And we've changed some of the memory tags, the way they're exposed to the application. For overlapped I/O, we have a function that basically creates a file that then when you do overlapped I/O, you can bind that file to an object. Like you create a file, and then you say, I want a completion queue, and my asynchronous operations, my completion queue are going to use this file object. So that you can explicitly, you can create multiples of them, and then you can control how you use them, control how completions are reported, and the most useful bit is if you know that you're running and you're affinitizing, you could have different files for different NUMA nodes, for example, so that you can localize where the completions are for particular resources and help balance things that way. One of the pitfalls of being fabric agnostic is there's things we can't do. We can't do RDMA atomic support because it's not supported in all the fabrics. Unreliable datagram, same thing. Multicast, send and invalidate, immediate data. Send and invalidate actually might work now, but there's mostly limited by IWARP, unfortunately. We'd love to see advances and convergence between the technologies so that we wouldn't have to be limited like this. From a availability perspective, we just released the version 2 of the headers this past December with our HPC Pack 2012 release. There's going to be support coming in WinOFED release in the 3.2 release coming up this May. The Mellanox 4.40 release coming second quarter. We'll also have it. And if you're someone that doesn't do Network Direct version 2 and you do RDMA hardware, there's space for rent right on this slide for you. So one of the things I want to show is right now in Windows, in the Windows OFED project, the primary user mode interface is eyeball. There's issues with using eyeball. There's no ABI versioning mechanisms. This seems to be kind of a recurring theme. And there's limited IHV support. When I actually wanted to test UDAPL, it took me better half a day to get it running up on over eyeball because of header mismatches, structure changes between the drivers that I was running and the DAPL implementation that I had built. Stan Smith at Intel ported UDAPL, at least the RC connection stuff, over Network Direct version 2. He did pretty much all the work. I helped him when he got stuck, but one of the main goals with this is it allows UDAPL to move around from basically get independence of the underlying drivers. It was a good test case for us to see whether the concept behind NDV2, making it easy to use outside of SMPI, were true. It was also, there's we're discussing potentially changing the format of the WinOFED project, and it was a good test case to see whether shipping just upper-level protocols would make sense. But and it worked. Dapple test just worked, but nobody runs Dapple test as in their business. So more interesting one to me was Intelmpi. Intelmpi on Windows uses UDAPL, which uses eyeball. And this was a good test to see, all right, so UDAPL works. Does an application like Intelmpi that's coded to UDAPL work without changes? Does it just work? And it does. I'm going to show some results. I want to make it clear that I didn't ask Intel for permission to show results because I figured they'd say no. And they're not endorsed by Intel. And there's been 0 performance tuning. And I ran the test once. So I did not account for noise or anything like that. There's jitter. My hardware configuration, I don't know if everyone knows or not, the HPC team is part of the Azure organization at Microsoft. We're chartered with bringing HPC capabilities to Windows Azure, which currently are not there. The idea is to make it so that your applications, HPC applications, can scale just as well if you ignore all the data movement stuff to the cloud. Once you have all the data in the cloud, they'll scale just as well as they would on premise. So our servers are pretty much what you'd expect from a HPC class server. Dual Sandy Bridge, QDR IB. It's running our Windows Azure OS. I ran whatever MPI we had on a share. So not the latest one, and whatever IMB was with it. And I ran ping pong, broadcast, some of the collectives. Test environment here was all of 2 servers connected to one another through a switch. There's 3 test environments I want to try. The first was on the host, right, physical machine running over eyeball. On the same host running over Network Direct, just to get a baseline of how does Network Direct compare to eyeball. And then up in our Azure VMs on the same host, but in VMs. Like I said, no averaging. I just ran it once, graphed it. So ping pong is actually kind of interesting. You can see the lines. The intent of the graphs isn't that they're necessarily legible, but that you get that the trends are that the lines pretty much overlap. That's the point I'm trying to make. It's a little weird that latency in the VMs is lower. I have no idea why. Broadcast, you can see again. So the graphs here, basically left is just the actual data, right is comparing to eyeball. So you can see the spikes. That's the noise stuff that I have not looked into. I'll go. So this here. Yeah. So the blue is Network Direct compared to eyeball, and the orange is the virtual machine, Network Direct in the VM compared to eyeball. So there's definitely jitter here. I'm going to go through this pretty fast because they're all the same. We're slower on barrier in the VMs, but the point really is that Network Direct, at least for the reliable connection path, works competitively with eyeball. It didn't require any code changes to get Intelmpi to work in our VMs, which was one of the things we were hoping to show. But it hasn't been scale tested. And the Intelmpi folks tell me they really want unreliable datagram. Woody was just outside actually talking to me about this. To which I said, we really want unreliable datagram support too, but we need hardware vendors to provide it. Which gets me to my next slide. So if you look at the Windows OFED project, it's been going on for quite some time. It's been instrumental in bringing RDMA support to Windows. With the work we did in the HPC team, it kind of planted the seed, piqued the interest of the storage team, and it was kind of the direct path to getting Network Direct in the kernel in Server 2012 and SMB Direct. It's been key to prototyping efforts. It's pretty much when we want to prototype something, we have all the business-y junk out of the way that lets us hack on the code. So that's been really valuable. It's been beneficial to participating IHVs. and it's where we came up with NDV1, NDV2. But there's limited IHV support. Mellanox is the only IHV that's showed up to play in the recent years. Part of that is our fault, because WGL certification of drivers has to be driven by the IHVs, can't be driven by an organization like the OFA, which means every IHV ends up having their own version that they go through WGL certification. We don't make participation in OFA a requirement for WGL certification. And this has unfortunately resulted in a spotty interop between WinOFED releases and Mellanox releases because of branch code. So one of the things I'd like to find out is what should we do with the Windows OFED project? Are we done? Have we accomplished what we wanted? Do we want to come up with a new way to get a driver full stack common across InfiniBand, iWarp, Rocky, all the different vendors? Or do we want to reuse the scope and say, all right, WinOFED is just going to do upper-level protocols like DAPL. We're going to have portability of all the IB diags through the Linux OFED interfaces. Get all our participating hardware vendors to commit to certain API support at the ABI level, but the drivers underneath that are free. One of the benefits here is, like I said, Microsoft can participate in the OFA. We'd like to continue participating. We'd like to see a little more value come out of this project. It's really kind of died down a lot. So pretty much what I'd like to see happen is more Network Direct version 2 providers implemented by the various IHVs. I'd like to see more applications use Network Direct if they're built for Windows. And then I'd like all of us to try, obviously some people just don't care about Windows at all, and that's fine. So the people who care about Windows to try to help redefine what Windows OFED should be and try to broaden the IHV involvement and then take advantage of this inroad to Microsoft from a development perspective, business perspective, et cetera. Have a slide for resources. They're kind of useless here. Thank you. Questions? I have Woody and Bill. I'm going to let Bill go first because he's your boss.
Well, first thing I wanted to thank you for showing Intelmpi results without asking me. I wish you could. It's a release product and you show whatever you want. I'm also really happy you guys did this project to show that things just work by switching out Fabric. That was the example we created 10 years ago. Just a big stable interface that people could add Fabric after the fact. It's not just the API, it's being built on commercial ISV apps carried forward. So it was cool to see that, especially in a virtualized environment like Jitter. Really neat that works. My question is about extensibility. Unreliable datagrams. You also said that the MD interfaces are extensible. So what prevents you from discovering that Fabric supports it and supporting that in one session as opposed to requiring homogeneity across all the Fabric support?
So I'll answer it in two ways. Number one, the first one is there's nothing to prevent driver vendor from providing interfaces that expose all the hardware-specific interfaces, whether it's UD or XRC or whatever, right? From a Microsoft perspective, there's a test. If we define an interface, it gives an expectation that we have potentially, if a driver is WGL certified, tested and certified that that interface works the way it should. So there's a test cost to us in defining extra interfaces for functionality that we can't necessarily use. And strangely enough, the people who have the money say that we shouldn't do stuff that doesn't get us paid.
So the quick follow-up
is there a mechanism for ideas that maybe aren't pervasive but are well-defined that people could come together and decide on a common API extension? Microsoft doesn't endorse it, but there's still a way for everybody to use the same one when they implement the same idea.
Absolutely, right? And that's really what I'd like to see the WinOFED project become, right? So that if there's interfaces that make sense and have broad appeal and applicability, that there be a single place where they're defined, where we get commitments that they'll be supported broadly by whoever can, right? And then see how it goes.
What's your take on R sockets, and would that be anything that you might consider including in the Microsoft distribution in the future?
So
there's a
I'm
Windows version of that now.
I work for Microsoft, but I work for the HPC team as part of Azure and not the Windows OS networking team. The official stance on layered service providers, which is the way that I think the RSockets provider is currently implemented, is they're deprecated from an OS perspective, which means that if you have issues and you call support, support's going to say, sorry, talk to whoever gave it to you. Are we interested in, I am personally interested in seeing that work.
Alternatively, do you have a sockets-based way to access high-speed fabrics?
No, we used to with WinSock
Right.
Direct, and it turned out that the socket API surface area and complexity was far too hard to implement properly and have it scale. It worked great between two systems.
So, I mean, I haven't looked at the Windows implementation of RSockets, but at least Sean's Linux one is totally user-space code. But you're saying it's implemented in a way that's not supported by Microsoft, or?
Yes.
Okay.
So if someone were to run RSockets, right, and ran into a problem and called Microsoft support, saying, "Hey, my socket application isn't working," the eventual conclusion would likely be, you're using an unsupported socket provider. Go talk to your socket provider vendor.
I see. Okay.
It's not ideal, but it's out of my hands.
If nobody else has a question, I have one more. You showed the performance data of running DAPL over eyeball and DAPL over NetDirect, and noise aside, it looks like they're basically parity, which is good. You didn't talk about the overhead of DAPL on top of NetDirect, yet you did a call for action to code directly to NetDirect. What we found at Intel is that the DAPL interfaces worked quite well. For the most extreme scale, the 250 nanoseconds of overhead that we see, on the smallest messages maybe matters, but for the broad case of commercial apps, DAPL served us quite well as a cross-OS interface. So I was just curious if others had experience with that and what your measurement showed.
I didn't measure it. It wasn't one of the design, the experiment variables that I cared about. I assumed that the DAPL overhead would be roughly equivalent, and if not, it would show up in the application data, right? So if DAPL was taking considerably longer, code paths or whatnot, we would have seen that. There are a lot of, there's opportunities for improving the code path on the speed path operations for Network Direct from the Network Direct interface down that haven't been done yet. Great, thank you.